Okay, we continue with the talk by Alexey Karapetyants, the Southern Federal University of Russia, and he will speak about Hadamard-Bergman convolution operators and generalized further spaces.
Well, thank you very much for the presentation. I will speak about this topic based on these three papers, two papers written with Professor Samko and one paper written with Smbata Gikyan, who was a postdoc 1 year ago at our university. And I will explain this notion of Hadamard-Bergman operator in next slides. But first of all, let me just mention few very simple definitions. I know that you very well familiar with the definitions, but just in case, let us state that we will be using this statement, this notion for the classical Lebesgue measure normalized. We will work with Lebesgue spaces. We will work with Fourier coefficients given by this formula, and with this space of whole holomorphic functions. Well, this kind of basic definitions, let me not explain more about this, all this. And so basically, what is the motivation of our study? If you introduce a notion that you must give an example of, or some examples, some good examples for operators in your class. So first example appears to be classical projection, holomorphic projection, which people call also Bergman projection. You see, if you consider, basically this formula is true, it's easy to check. You can write ZW here, or you can write ZW here, and maybe this is a good idea to understand that such type of operator possesses some kind of commutation, you see, and that's why it's worth to study this class of operator when you replace this particular function with a general function. Well, for the Bourbon kernel, this general function is here. It's a very simple general function here. So, given taking this g of z, you will have a particular case of our operator Bergman projection. And of course, all these operators are multiplier operators. And you can ask why we don't use a technique of multipliers for the study of these operators. Of course, people use very much the technique of multipliers, and there is a book, recent book by Vukotic and others, written very well on the multipliers here, Taylor coefficients, multipliers, etc. There are a lot of results, but multipliers from one side are good, from the other side not so good. For instance, you cannot use this technique when you work in a space with no lattice property. What I mean? I mean, if a function g belongs to your space X and function f such that modulus of f less or equal than modulus of g, then f also belongs to the same space X. So, very simple example of a space with no lattice property is a Hölder space. So the technique of multipliers is useless for the study of operators in Hölder spaces. And this would be our most important application of our theory, because I will divide my talk in two parts. First, I will speak about these Adamar-Bergman operators, and second part will be devoted to the study of some operators of this type in between Hölder spaces, generalized Hölder spaces. Okay, so this is the first motivation. This is the second motivation. We will also have another examples. For instance, operation of fractional integration. You see, Bergman projection is when you have integral over unit disk f of w 1 minus zw bar squared dAw. Being considered on space of holomorphic functions, this is identity operator. So when you subtract something like alpha, you have this kind of improvement. So you actually have fractional integration. It's written here. it's also another example of operator in our class. And of course, once you study fractional integration, you can rewrite it in multipliers in terms of this power series. Then you elementary can recover the fractional differentiation operator. Okay, and you will have this identity. Okay, so more general examples provide by these more general weighted operators of fractional integral differentiation. And this weight, this kind of generalization of the previous constructions, but this weight is very important because this weight works very well when you apply it to a Bourbon kernel. And using this way, you can have this substitute of the semigroup property. You see, if you consider just unweighted I alpha, I beta, then you cannot I beta. You cannot have the same with a certain gamma. So you can use this weight to arrange for this substitution of semigroup property. I mean property 4.3. Well, again, this is an example. Sorry. This is an example of our Hadamard-Bergman convolution operator, because it can be written in it can be written in this integral form, and also we can give the integral representation for the operation of differentiation. Well, this kind of motivation, and now let me just say that what I will be speaking about is operator of the form 6.1. 6.1. So you take two holomorphic functions g and f and construct this convolution, which we understand as a limit for arbitrary function, for arbitrary holomorphic function. As I said, Bourbon projection you will recover when you take g of w equals to 1 over 1 minus w squared. Okay, so this would be the idea. To generalize operators of Bourbon type, and so that's why we have in our title a Bourbon name, in the name of Hadamard-Bergman. Okay, and of course this symmetry property gives us an idea that this kind of sort of convolution, and we can expect good properties when we study the entire class of such convolutions. So next question, why Adamar? Because, as I said, these all operators are multiplied operators, and we know very well the notion of Adamar product composition of two holomorphic functions. If you take function f in its Taylor series, and if you take function g in its Taylor series, then the composition is given by this Taylor series. You just multiply fn and gn, and basically you can also here fix a function g, consider it to be a kernel, and think that you have an operator that acts on a function f. And people say if gn go to 0, then people say that it's kind of generalization of fractional differentiation. It's natural. And if gn go if gn go to infinity, then we'll have differentiation. If gn go all go to 0, then we'll have generalization of fractional integration. But in general, people call this construction Adamar product composition of two holomorphic functions. I would like to recall you that fractional calculus appeared first in complete analysis, and then it came, the research came to real analysis. What else? Well, for the understanding of this construction, as I said, that we will understand the integral in improper sense, because we have this very nice identity 8.1, and from this you can see that you can easily put r equals to 1, nothing happens. This will be convergent because both functions are supposed to be from the space of holomorphic functions. Okay, and that's why we know that every integral of this type exists as a proper integral, as a limit, and we will understand from now on, we will understand our constructions in this sense. Okay, so I already gave you this definition. So the product of two functions, f and g, we will call Hadamard-Bergman convolution. And I explained why Adamar, and I also explained why Bergman. Also, I said, and I will repeat it, that sometime I will consider it as a convolution of two functions, f and g, or in most cases, I consider g to be fixed, so I consider operator generated by this function g. Okay. So I already said this. Let us consider g to be fixed, and we associate to a function g associate an operator k. So again, as a motivation, this is generalization of Bourbon and even more general tuplet operators. Every such operator has a multiplier which can be easily calculated in this form. Okay, it's clear. But also, if you have a general multiply operator k, which acts on the basis in this way, then you can easily construct corresponding kernel by applying this operator k to the Bourbon kernel. So this is a way how to construct the integral representation for arbitrary multiplier operator. So again, we have one-to-one correspondence between Hadamard-Bergman integral operators and multiplier operators. But the reason why we study in integral form, I explained, because our intention to study, these operators in some other spaces, such as Gödel spaces, when you cannot use technique of multipliers. Okay. Also, once you consider convolutions, then you can ask whether it's worth to study kernels which are not holomorphic also. It's also a nice subject to study. So let's see, let's think for a moment that k is not holomorphic. Still, you have this multiplier structure. Still, you can calculate multipliers for this operator. And also, if you have this operator with non-holomorphic kernel, then we can also calculate the corresponding holomorphic kernel that will generate the same operator. The way to calculate is also simple. You just apply a Bergman projection to the non-holomorphic kernel k. So basically you can rewrite this operator 13.1 in this form with a new kernel given by the application of Bourbon projection to the non-holomorphic function k. Okay, so what else? Again, more general construction. What if we still have a holomorphic kernel, but then also multiply by a certain non-holomorphic part, like in this form? And actually, you will have the same symmetry property. It appears that this radial function does not affect to this symmetry property, which is good, which is kind of class of convolution operators with some symmetry property. It's worth to study this class, but maybe the main reason for such operators is then inside of this class, inside of this class, you can find tuplet operators with radial kernels. Tuplet operator is given by this formula. You take function you take galomorphic function, you multiply this function by a non-galomorphic symbol, you go out of galomorphic space, and then you apply Bourbon projection to come back to the galomorphic space. So that's what people call tool-space operator. It has this integral representation, and as you can see, it can be written. It is written in terms of Hadamard-Bergman projection. So actually, we had already just one paper with Yari Tatskin on these properties of on connection of these operators with radial kernels and compactness and Berezin transform, and we used some properties that I will be speaking about in my talk, but I will not be speaking about this particular article. It's maybe a subject for another talk, but what I want to say is that this technique works very nice. So another example of operator in our class is so-called operator with a homogeneous kernel. If you take, you can, well, I didn't present here a calculus, and just by change of variable, you can start with Hadamard-Bergman operator and go to this operator written in 16.1. So if you take a look at this kernel and rewrite it as a two-variable kernel in this form, then you will find out that this is nothing but the operator, homogeneous operator of degree -2. So people call operator to be homogeneous of degree -2 if for any scalar you have this property, and for any rotation you have this property. And you see, we can use people studied homogeneous operators with homogeneous kernels in real analysis. We know very well boundedness criteria, etc., many theorems. But if we apply this theorem, this theory to this particular case, then we will not have the ideal result. I mean, using the property of holomorphic functions, you can have better result. You can improve the general result for homogeneous kernels, and it's understandable because working with holomorphic functions, you always have some additional tools to imply in your proof. And that's what about I'm saying about, for instance, this Young theorem. Under these conditions, if K kernel is LQ function, and if we act on space of Bourbon, on Bourbon space AP, then we have this Young theorem. And the proof is based on interpolation, on known result, but at the end, you have such construction, such type of construction, integral over D, f of z w, dA of w, and the idea is, in case of holomorphic function, what you cannot do in real analysis, you just can estimate by norm of f in L1 by maximum principle. You see, so you can ignore the z. You can use the property of holomorphic function, estimate by this inequality, and then get this nice theorem. So these things sometimes are given to you in a very simple manner when you just apply some classical theorems, complex analysis, and so we can improve the known results for operators with homogeneous kernels in this particular case. Okay, well, now I turn to my second part of the talk related to Gödel spaces, generalized Gödel spaces. But before, I have to introduce notion of modulus of continuity. Actually, I will introduce more general notion of modulus of continuity, but it will be at the end of my talk, because I want to explain main results in a simple manner, so I don't want to have complications. So let us just start. I'm sure that almost all of you know this notion of modulus of continuity. A function omega is called modulus of continuity if these conditions if it possesses these conditions, 1, 3. And also I will use the following Zygmunt type conditions. Sometimes people call this condition sometimes people call Dini, this condition B1, sometimes Zygmunt type conditions. Doesn't matter. So a typical example of modulus of continuity is this power logarithmic function, for instance. Okay, so speaking about Gölder spaces, basically we will deal with two classes of Gölder spaces. One class is given by classical formula when you just subtract f of z minus f of w less or equal constant times omega calculated at the distance between z and w. So definition is here. This definition just for a measurable function, of course. And then to have holomorphic, you have to intersect where it's here, where it is. It's not written by formula. It's not written by formula, but as usual, if we speak about holomorphic space, that the holomorphic space A omega over unit disk is intersection of a deck space these holomorphic functions. Okay, so the definition is clear. It's here. The semi-norm is given by this formula, and the norm is given by this formula, and of course the semi-norm in the holomorphic space is the same as in non-holomorphic space. Also, second type of Gölder space, sometimes people call it Besov space, is given by the behavior of the derivative near the boundary. So now, because we take derivative, we already have to be inside of holomorphic functions. So let us take a holomorphic function that satisfies this condition. Then we will say that this function belongs to the space B omega. So I will be using this of A omega and B omega spaces. And basically these spaces are almost the same, except two cases. Except two, I mean, not two cases, except some particular cases. But basically, you can see this remark. If you have, where is, no, I'm sorry, I have to come back to Zygmunt. So this would be the first Zygmunt condition. This would be the second Zygmunt condition. Okay, so I will call it first, I will call it second. Okay, so if omega satisfies first Zygmunt condition, then the space B is inside of the space A, and vice versa. If omega satisfies second Zygmunt condition, then you have the inverse inclusion. Now you understand that if both conditions are satisfied, then you have the same. So the space A omega and space B omega are the same, which is very good because, I mean, sometimes working with derivative is much easier than when you just have to prove something for the difference f of z minus f of w. Okay. So let's start with theorem on mapping of fractional operator in A omega and B omega. I have to recall you, well, actually it's written here, the fractional integration E alpha f of z is written here. So in this formula you have a generalization of the separator when you have a general characteristic. If, for instance, here it is, if your characteristic is this function, then you obviously have this particular case. You have minus alpha. Okay, but let us consider this generalized operator. We can of course call it operator of fractional integration. and the theorem is here. So how it acts? Under these conditions, on modulus of continuity, let me not read these conditions. It's written here very clearly. We have the following. We have the following mapping property. So this fractional operator maps the space B omega to the space B omega alpha, and B omega A, and omega A is nothing but this product. Well, just to explain you, if you have this particular case A1 minus Z equals to 1 minus Z to the power alpha, the case of classical potential, then omega A, actually we will call it omega alpha, is nothing but h to the power alpha omega of h. So you just improve your space by alpha parameter, you see? Okay, under some additional condition that omega satisfies second Zygmunt condition and omega A satisfies first Zygmunt condition, you have also mapping property in space A omega. You see, as I said, the space B omega kind of easy to study, and it will be always that we will have more conditions when we state something for the space A rather than for the space B. Okay?
Sir, what is the capital point?
I'm sorry, this capital omega, it's not written here, stands for the set of all modulus of continuity. So I must write here, let A star and omega are modulus of continuity, that's it. Sorry, you're right. In particular case, when you study this operator, you have not just action property, but also this identity. I mean, it maps the space onto the space A omega alpha. Okay, and in this connection, we use this integral representation, this kind of formulas, etc., etc. Just for example, in classical case, if you apply operator to the Gölder space A alpha, then you will have, as a result, you will have the space A lambda plus alpha. So you improve by alpha, and you must take care of the issue that alpha plus alpha must be inside 0 and 1. So this actually is what about the Zygmunt conditions. I just illustrate on this simple example. Okay, now still more complicated case. How much time I have?
10 minutes.
Okay. Let's go further and introduce variable Hadamard-Bergman convolution operators. So basically, you also have a function g, but now this function g will depend also on this external variable z. You still have this almost the same. You can understand this as a proper integral. You can develop the same theory, etc., etc. You have this symmetry property. Even this z does not affect on this symmetry property. You cannot write as a multiplier already, because if you try to do this, you will have not power series but functional series. And of course, you can introduce operators of fractional integral differentiation of variable order. You can also write not as Taylor series, but it's already written as functional series because z is here. You see, you can do this, but you cannot construct inverse just moving the sides. I mean, just inverting this construction, because as usual in the theory of operators of variable order, it is known, it works by Samko in 1996 when he and his colleagues tried to construct inversion of operators of integration of fractional of variable order, then it's not possible to do it as in case of constant order. It's possible up to some compact operator. Maybe in this theory also we can do the same, but it was not subject of our research. I mean, just try to construct inverse operators in similar form and find that the composition will give you identity operator plus some compact operator. I guess it can be done. So since we are speaking about generalized spaces, already generalized operators, we have to introduce the notion of variable modulus of continuity. So let me don't read this because we don't have time. The idea is just to list all properties which are uniform with respect to the z variable. So just we ask that all properties will be uniform. It's written here. So in the same sense, we can introduce variable modulus of continuity, and space is A. I guess it's here. Space A is written by a simple formula, by the same formula, just use modulus of continuity of function. And also we can introduce space B in similar terms by using this construction. And let me just give you one remark. Why it's of interest to consider these spaces? Because you see, when you work with Euler space, you always think about applications to PDEs, to some boundary value problems, and it's quite natural when you impose boundary conditions. People sometimes take functions from Euler type of spaces, so it's quite natural to have different type of Euler behavior when you approach to different points. And this is what is achieved by taking this modulus of continuity, omega, which depends also on the variable. Inside this case, you can always recover the classical case, omega of h, the classical case, which I explained before, and also a particular case when you have a variable Gölder space, variable Gölder space. This is the general case. Okay, so I guess it's kind of natural to study this type of Gölder spaces when you have different behavior, of your function when approaching to the boundary, and you can impose different types of Gölder continuity on the boundary. Okay. So also we have to generalize Zygmund conditions, etc., etc. Let me just not waste time on this slide. Also, we can prove that one space is inside the other under first Zygmund condition and vice versa under the second Zygmund condition. Okay, and of course, when both Zygmund conditions satisfied, then you have the same spaces. And operators, which is similar to that I spoke recently, now it's generalized operator with characteristic that depends on the variable. So under some general conditions, you can have I'm sorry. Under some general conditions, you can have that doesn't work. You can have this theorem. You can have this theorem. So let me not read this statement. Some assumption on modulus of continuity. Okay. So this would be the result, and the result is in the case of real part of alpha is not 0. So this is just particular case of the previous theorem, just to explain what happened when you take power logarithmic characteristic. I think I don't have time, but for instance, this is a corollary of previous theorem. The conditions, of course, are simpler. Of course, these conditions are simpler in this particular case. And now let me go to another example, and I will speak about another theorem, and I will speak about only this particular case of variable integration. And let me explain what does it mean degeneracy of the real part of alpha. You see, in previous slide, I wrote that real part of alpha of z is not zero, infinitum. Okay. Of course, in previous example, in previous theorem, I have more general operator which is constructed by using characteristic. But in case when this characteristic, as I said, 1 minus z equals to 1 minus z to the power alpha, then we apply this condition. That's what we mean. But now we allow this real part to be zero. What's going on with this condition? You see, if you take a look at this operator, and if formally you put here 0, then you will have a Bourbon projection, which is identity operator, so which does nothing. When you put here alpha positive, then you have integration, does something. But if alpha is variable, then what happens? What happens when alpha comes close to 0, and then go out, and also to 0? So it's not easy to understand what's going on. So in previous case, we didn't care about this situation because we imposed strong conditions on modulus of continuity, and these conditions allowed us to work with space of B type. When you work with space of B type, you work with derivatives. You don't care about integrals. So in this case is easy, and we may not think about this issue. But now we want to reduce conditions on modulus of continuity, and so we are obliged to work with integral representations. And in this case, we face a problem that we must assume that infinitum of real part of alpha is positive. So from one side, we cancel some conditions on omega of modulus of continuity. From we have stronger result, but if we don't want to impose this, if you don't want to impose these conditions, then, for instance, we work with this Zygmunt type estimate, and you can see the alpha is here. You have to avoid this. You have to avoid this case when alpha approaches to when the real part of alpha approaches to 0. But I'd like to stress and attention that well, this Zygmunt type estimate, and based on this Zygmunt type estimate, we have this theorem, final theorem, and I'm almost done. But I'd like to stress this idea very clearly, that this situation is very interesting to study in the future, because the behavior of the rate of behavior of this alpha may affect properties of mapping properties of the corresponding potentials. Well, thank you very much.
If there are questions,
could you go to the transparency before? You study Bergman projection.
First slide.
Yes. So so basically you say that when the operators that because there is an operator who's diagonal, this operator can be represented by a Bergman projection, no, something like.
No, I didn't say that. No. Maybe you refer to the. Let me see. I understand. It's theorem about if you consider a general operator given in multiplier form, then you can construct a kernel, and you can give this Hadamard-Bergman convolution. So the kernel is constructed by application of this operator to this Bergman kernel. So this function gives you this convolution: g of w, f z of w bar, dA of w, and this will give your operator k applied to f at the point z.
The question is, what about if the operator k is triangular?
Triangular? I didn't think about it. It's a good question, maybe.
This Bergman operator is bounded on some space of analytic function.
Yes, bounded is known. It's bounded it's bounded in Lebesgue space for p strictly between 1 and infinity. In many other spaces, we studied also boundedness on. People also studied boundedness on other spaces, Orlic spaces, Morris spaces. Yeah, there are many conditions for boundedness. But the idea is not study Bergman projection. I mean, the idea is to study the more general classes when you take not just this particular function as a kernel, but just a general function.
Thank you. More questions? If not, then thank you very much again.